Hi, welcome to Demystifying Math. In this lesson we're going to be working on series representations for functions. To start off, we want to find a polynomial that closely represents the function e to the x, centered at 0. We can do this using the Taylor-Maclaurin method for finding polynomials. Since we're centered at 0, it's really the Maclaurin method. So with the Maclaurin method, what we want to do is find the derivatives of e to the x. When we know that the derivative of e to the x is itself, then we're going to take those derivatives and evaluate it at 0. So e to the 0 is 1. So in our model for our polynomial, where it has the function evaluated at 0, the derivative at 0, the second derivative at 0, and so on, we're going to replace each of those with a 1. So we end up with an approximation of e to the x as 1 plus x squared over 2 factorial plus x to the third over 3 factorial and on to x to the n over n factorial. Let's take a look at some of the polynomials and compare them to the function e to the x. So in this first graph we have the first 3 terms of the Maclaurin polynomial. It is a parabola, but notice that at 0, the two functions have the same value of 1. As we move away from 0, the two graphs start to separate. So what we're going to do is add on another term of the polynomial. When we added on the fourth term, you can see that the two graphs are a little bit closer together, so it's a little bit better estimate for e to the x. Let's add on another term. Here we have the 4th degree polynomial, and you can see from this that as we move away from 0, the polynomial is a better estimate of e to the x. Let's try again, and this time we have an 8th degree term polynomial. So in that case, you can see how closely they match up on the right side. On the left side, they're still a little bit further apart. But if we took this out to infinity, the polynomial would be exactly the graph of e to the x. So if we take it out to infinity, we can rewrite the polynomial as a series. So we have the sum of n equals 0 to infinity of x to the n over n factorial. We call this e to the x expansion an elementary function. We can take the e to the x function and use it to create series for other functions that are similar to e to the x. For instance, if we had the function e to the 2x, the only difference between the two functions is that we took x and multiplied it by 2. So we're going to do the exact same thing to the polynomial. We're going to replace x with twice x. And you can see pretty quickly that we have a pattern going of 2, and then 4 is 2 squared, 8 is 2 to the third, 16 to the fourth. So we really have 2 to the n, or 2 times x to the n over n factorial. And we're going to take the sum of those terms from 0 to infinity to get a close approximation of e to the 2x. Actually, if we go out to infinity, it will be the same graph as e to the 2x. Let's go ahead and verify this by finding the Maclaurin polynomial for the first few terms. Again, we're going to take the derivatives. So remember that e to the 2x is a composite function. It is its own derivative, but then we take the derivative of 2x, which is just 2. Evaluating the first derivative at 0, we get 2. Evaluating the second derivative at 0, we get 4. Let's do a few more so we can see what the pattern is. And you can see that these coefficients are all powers of 2. So we can rewrite the polynomial as 1 plus 2x plus 2 squared or 4x squared over 2 factorial. 2 to the third or 8x cubed over 3 factorial, which gives us the sum exactly how we found it by using the substitution into the e to the x expansion. For some functions, using the Taylor-Maclaurin model doesn't work too well because the derivatives are undefined. for instance, if we had the function e to the square root of x, and we tried to find the first derivative, we could do that, but then we can't evaluate it at 0 because it's going to be undefined. So instead of using the Taylor-Maclaurin model, what we're going to do is use the expansion that we found for e to the x and replace x with the square root of x. And we obtain this function, 1 plus x to the 1/2, replacing x with square root of x and x squared just gives us x. Replacing the square root of x in the x to the third gives us the square root of x to the third, or x to the 3/2. So we can see a pattern in our exponents pretty easily. That gives us x to the n over 2 over n factorial, and we're going to take the sum of n equals 0 to infinity. Let's compare the graphs to make sure that what we did is correct. So looking at the e to the square root of x in the first 4 terms of the polynomial, you can see that they are very closely related near 0. You can also see that they have the same domain. They both involve the square root of x, so the domain will be from 0 to infinity. Taking a few more terms, you can see how closely related these are. We actually had to go all the way out to about x equals 10 to start to see a difference between the two functions. So this is a very good approximation of e to the square root of x. Again, if we took this out to the sum, to the infinite sum, it would be exactly e to the square root of x. Okay, thank you for tuning in to Demystifying Math, and I hope this helped you with some of your series questions.